Hi and welcome to video 11 on this video series on Integration, Application of Integration, Unit 4, Topic 1, Specialist Mathematics. And we're going to be talking today about the Simpsons Rule, which, to be honest, if you have done in your work in math methods, the trapezoidal rule, well, the Simpsons Rule is fairly simple, so this shouldn't be too bad. So let's start with, and I've obviously built some learning goals and success criteria slightly over the top of my title, which I'll need to backtrack and fix up later. An area under a curve, or an estimation of a function that has a constant in it. So when I say function that has a constant in it, f of x just equals 7 or something like this, this is a rectangle, and we've done that rectangle method. So the rectangles method early in trapezoidal rule gave us that. An area under a curve that was linear, so this is where we had the curve here, and we'd use linear subsections, produced these shapes, which were trapeziums. So this is the trapezoidal rule, uses a uses a linear function estimation technique. A quadratic function technique is the Simpsons rule. Now, Simpsons rule turns out to be slightly more complex than trapezoidal rule, but not much. If you go beyond that to cubics, you'll actually find that the function gets more complex. In some cases, it's quite hard to determine, and it doesn't really provide us that much more accuracy, so it's not really worth doing. But what we're going to be doing today is estimating the area under a curve like that using sections of a quadratic, where that is part of a quadratic, and we find the area under the quadratic, and that is part of the quadratic, so on and so forth. So we're going to be using sections of a quadratic. But here is our formula. Now, it comes in various different forms. Typically, you can sometimes see it with n's again for h0 and hn, and then 4 times the odds. You see this, 0, 3, 5. And 2 times the evens. So in fact, I don't think we use n's often. Often you still just have h0 and hn and odds and evens. So you'll see variance on that. And I have got this slightly wrong. That should actually have a w over 3 for the Simpsons rule. So there's our formulas, but we're going to go ahead now and prove the formulas so that you know what to use and how to use them, and you might need to revert back to this proof in some harder questions. It's going to be a fill in the blanks proof because it's quite complex and I might not remember it all. So in yellow we have the fill in the blanks parts, and I'll be writing those in black because obviously it's there. We're going to use a function here. I've drawn it. We're going to find an estimate of the area between A and B. I've got all my heights as y0, y1, y2, etc. And these are my coordinates. x2, so this is x0, and it goes to y0, so that's y0 there, so on and so forth, of this function. Now I'm going to use the first 3 points to model a quadratic, because we know that we can use 3 points to model a perfect quadratic. And we just use simultaneous equations to do that. So I've substituted in for my y0, 1 and 2, I've got x0, x1, x2 into the standard quadratic form. And I also know that x1 is the midpoint of x2 plus x0. I'm making that statement that I'm choosing to have them evenly spaced along the base. So I can rearrange it to get this. And I'll use that. So to find the area under the quadratic, so this is not a quadratic, but the estimation is a quadratic, which you'll see if I draw a quadratic between those 3 points, it's going to be pretty much on that curve. I need to find the area between x2 and x0 of the quadratic there. And so I need to do, what is that, ax cubed over 3 plus bx squared over 2 plus cx between x2 and x0. And I'm going to multiply through by 6, so I'll have a 6 out the front here, and now I'll have 2ax cubed, 3bx squared, and 6cx. I've just taken those fractions because they're annoying and removed them. And that 1/6 is going to carry, by the way, so 1/6 the whole way down. We'll see how far it goes. I might move it back in a little bit later. So we've got this now, and I've missed a highlighting here, but ultimately I've substituted in my x2 and my x0. So this is 2, this is 3, this is 6, 2, 3, 6. That hasn't changed. And I'm going to take my 2a, and inside here I'll have x2 cubed minus x0 cubed. And inside here I'll have 3b x2 squared minus x0 squared. And inside here I'll have 6c x2 minus x0. And now I'm going to do some factorizing. It turns out that this is x2 minus x0 times this stuff. So you're not really expected to know that cubic factorization, but it's true, believe it or not. And I've still got a 2 there. And I've still got a 3 here. And it turns out that this is x2 minus x0 times by x2 plus x0. You know that. That's the difference of two squares. And I've still got a 6 here, and I've got x2 minus x0. So that means I can now take that x2 minus x0 out the front as a common factor, leaving me with a times that, so it's 2a, 3b times that, and 6c. Now if we go back up the top, something I've done in between is demonstrate that the width is the difference between our two ordinates, and in this case, because we're doing it for 3 points, we've got an ordinate here, an ordinate here, and an ordinate in between. But if I do x2 minus x0 and then divide that gap by 2, I get this green width. I get one of those widths. So I'm going to write down that my width is x2 minus x0 over 2. And I've got 1/6 times this, so I now have 1/3 times the width, which is width over 3. And this flows the whole way down, and you'll see it meets up with my formula. And the other yellow bits that I need to evaluate are that I'm going to break this up deliberately to head towards a y0 and a y2, and what will be left is a y1. So let's have a look. First, to get to my y2, I take out, well actually first I expand the brackets. I get 2a, 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 3b, 3b, and 6c. There's my bracket expansion. And once I've expanded the brackets, I take out enough values to get a y2 and enough values to get a y0, and that leaves me with 1ax2 squared. I've still got this one here, which is 2ax2 x0, and then I've got 1ax0 squared. And if I take out a bx2 and a bx0, I'm left with 2bx2 plus 2bx0. And then I take out a c and a c, I'm left with 4c. And so next, I recognise that this bracket here goes to there, and it gives me just a y2 from there. And I've got a y0 from there. And in actual fact, it's better if I swap those around. So even though we've done it the other way, it will work out better for us in the end if I swap it around. And here, that value just here can be broken down into the a comes out the front. We've got x2 plus x0 squared, and 2b times by x2 plus x0, and 2c, I should take that out, and 4c just remains 4c. Now x2 plus x0, of course, is 2x1, so this becomes 2x1 squared, and this becomes 2x1. And so I've got y0, y2, y0, y2, and here you'll note that 2x1 becomes 4a x1 squared plus 4b x1 plus 4c, which becomes 4 ax1 squared plus bx1 plus c, and that becomes 4y1. So I'll write that down as 4 ax1 plus squared plus bx1 plus c, and that becomes 4y1. And now I rearrange that, I pop that into the middle, and I've already swapped the y2 and y0 around for my pre-designed notes, and I get this value here. And so the area evaluation for the first two is width over 2 y0 plus 4y1 plus y2. And for the second one here in green, it's w over 3 y2 plus 4y3 plus y4. And so I've got here y2 and y2. When we put those two y2s together, we get 2y2. So I've got y0 from the first one, 4y1 from the second one, then 2y2 because I've got the 1 from the first grouping here and the one of them from the green grouping. And then I've got 4y3 from the green grouping, and I've got 2y4, one of them is from the green grouping and one of them is from the blue grouping. And of course the blue grouping is the next three ordinates. And it goes on and goes on until I run out, depending on my gap. Which leads to this formula, which is the one we talked about earlier, however you want to set it up. So we've got this variant, we've got this variant, we've got this variant, whatever works for you.